Hi everyone, welcome. Today we're going to be talking about cylinders and quadric surfaces. When we look at cylinders, we naturally think of this cylindrical shape where either the ends are open or the ends are closed, and they're typically capped off by circles. However, as we are going to keep diving more and more into these three-dimensional surfaces, we want to develop a definition more for a cylinder. So on screen here, you see that I have a definition that says a cylinder is a surface that is generated by moving a straight line along a given planar curve, while holding the line parallel to a given fixed line. Okay, so that says a lot. Now, more specifically, on screen here, I have that your surface here is the blue surface. That's my cylinder. As we go through the definition, we need some lines that are moving through that will be generating this specific surface. So we have this generating curve, and that's going to be the curve in red. And as we start moving, or as we start generating these curves or these lines are actually making my surface appear. So this curve that we are moving along the YZ plane, this curve is going to be then generating all of these lines, which will then generate this surface. And again, this is how we classify a cylinder. So again, notice when we're talking about cylinders in RSpace 3, it's kind of ambiguous when we mention a cylinder. However, when we mention a right circular cylinder, then we're talking about that cylinder that we knew back in geometry or in algebra class. So we're using the word cylinder a little bit more loosely here. Again, it can identify surfaces. Now, we're also going to be looking at traces. And the definition I have on here on screen for the traces is that traces are a collection of curves obtained by intersecting the surface with planes parallel to one of the coordinate planes. This gives a cross section of the surface. Now I have this nice picture here for you all. Okay, so this is a nice picture that I made on GeoGebra, and this hyperboloid is a hyperboloid of one sheet. Notice it opens on both ends, both in the positive z direction and in the negative z direction, and most of these cross sections or these traces are traces of circles. Depending on what z value we start identifying this trace, we are going to have a different type of circle, meaning it might have a different radius. And so what we're in the process of doing in this particular section is identifying these traces. That way we can start generating this surface. So let's see if we can then identify this surface. Again, looking at the traces, the definition for traces says that it's going to be a collection of curves obtained by intersecting the surface with parallel planes. Okay, so, and they're going to have to be parallel planes to a specific plane. So if you look at the first graphic on the left, that shows the XZ axis, which means all of these traces that I have on screen here, they're all denoted with the color green, and all of these traces are parallel to the plane XZ, meaning they exist on the y-axis, or the y-plane. As soon as we find a plane for y, say y is equal to 1, y is equal to 2, then we're able to start generating these parabolas that we see here. The second graphic shows the plane, or the view from the z-axis. This means that we get a quick snapshot into what is the x and the y-axis. So all of these traces are now parallel to the plane xy. Okay, so all of these traces exist on some z value. Same thing's going to happen for this last graphic. On this last graphic, we see that we have the YZ axis. So again, we are viewing this from the x-axis point of view. This means that all of these traces are then parallel to some equation. X is equal to 5, x is equal to 4, x is equal to 3, x is equal to 0, so on and so forth. So viewing these three traces, we now get to try to envision this particular surface in R space 3. This surface is actually a little bit on the harder end to try to identify. It's one of my favorite surfaces, but again, it's a little harder to identify. So let's go on to my old friend GeoGebra, and we're going to see how that's going to help us out in identifying what this surface is, given these 3 points of view. So here we are. I have GeoGebra here. Awesome. So what I'm going to start looking at now, again, is going to be those traces. So I know I have a trace that is a hyperbola. And here are my hyperbola traces. All right, let's shift my view a bit. And remember, these traces were from the z-axis looking down below. So again, here are my traces. Okay, that's looking good. Now I'm going to superimpose my other traces, which was, number one, a parabola. And this parabola was viewed from the xy plane. Or sorry, not the xy plane. These parabolas were viewed from the xz plane. Notice it's getting a little convoluted, and we'll kind of keep that in mind. But as you can see, all of these traces, no matter how we draw them, they're intersecting one another. It's creating a surface. Going on to the last one, the last trace, here we are for parabolas again. And this was viewing directly from the y-axis, directly from the x-axis, which means these are from the y and z plane point of view. So notice we have two traces that are parabolas and one trace that is a hyperbola. Again, it's getting very, very convoluted here. So what we do now is we try to just fill in the gaps now. We start shading everything that we see. When we do this, we get this new surface, or we get this surface that we then start looking at. This is a hyperbolic paraboloid. And again, this is a hyperbolic paraboloid simply because one of the traces is hyperbolas and the other two traces are parabolas. Hence, hyperbolic for hyperbolas, paraboloid for using the parabolas as some of your traces. Now again, trying to envision this is a little bit more on the difficult side. So I'm going to show you a brief snapshot, just a smaller picture into what this actually employs for us, or the visualization that we will need. Okay, so again, here's that surface, and again, using that surface on GeoGebra, it's kind of hard to see because of the improper shading. However, if I think about this slightly different, check this out. We can actually see it a little bit better here. And this, again, is your hyperbolic paraboloid. Again, it has that Pringle chip feel. Or if you don't know what a Pringle is, it kind of looks like a saddle. And those are the saddles that we, put on horses or animals so that we can ride them. Now, we are going to be investigating at a later time what values give us, or what coordinates give us this saddle point. Because as you can see, it is neither a maximum nor it is a minimum. So when we start incorporating calculus into this, will then be in the process of finding what values give us a maximum or what values give us a minimum. Wow, I was about to invent a new word right there, miximum. Okay, let's forget about that. So maximum or minimum values, and because this is R space 3, we're going to have one more choice. Is it a saddle point? And as you can see here, yes, we do get saddle points. So this is, again, one of my favorite pictures. Now, as we go through the course, I am not going to have you draw some of these pictures for these hyperbolic paraboloids. As you can see, they are very difficult to try to generate. Though, if you can generate one, kudos to you. That is amazing. So take some time and start practicing some of these surfaces by hand. So we're going to go through and we're now going to identify some of these surfaces that we will be working with. All right. So I'm going to go back to the whiteboard and write down the answers, or write down the names there, names and the equations. Okay, so before we move on, I want to identify the surface. The surface is a hyperbolic paraboloid. Awesome. Now, if you stick around, I'll give you the equations and those surfaces in just a bit. All right, so here we are. By the use of internet magic, these are now the common surfaces that we will be looking at when we're working in multivariable moving forward. We're either going to be working with an ellipsoid, hyperboloids, and this is going to be a hyperboloid of 1 or a hyperboloid of 2 sheets, an elliptic cone. And remember, these elliptic cones don't need to necessarily have these elliptical openings or these ellipse openings. They can have circular openings, and in that case, it's just a small case of, it's just a special case of an elliptic cone, which will be a circular cone. And we can have paraboloids. We can either have an elliptic paraboloid or a hyperbolic paraboloid. We can also have circular paraboloids. However, circular, again, it's a special case of the ellipse. Therefore, we still classify it as an elliptic paraboloid. Now, within this whole process of multivariable for the next few weeks, we're also going to be identifying, or better yet, some of the problems are going to be given a specific surface. Some of the problems will say you're working with an ellipsoid bounded only in octant 1. Or it might say, hey, you have an elliptic cone, but I only want you to focus where the y values are negative and the z values are negative and the x values are negative as well. So then you have to find that octant and then represent this specific surface on that octant. So there are different ways that these are going to be presented. Now, before we get into that, I want to show you the visualization of all of these surfaces. So follow me on to GeoGebra. Okay, so here we are on GeoGebra. Your multivariable calculus book that I have on GeoGebra, I gave you all the link access to that book that I created on GeoGebra. And one of the applets here is the applet of quadric surfaces. If you go to that applet, you will then be able to see that I have here depicted a cone, and you'll be able to see what the equation of the cone looks like. And it's given by this equation on screen on the left. You will also see an ellipsoid. So there you are. You will also see a hyperbolic paraboloid. So hyperbolic paraboloid, again, looks like a Pringle chip or a saddle. A hyperboloid of 1 sheet. Notice it's a hyperboloid, and then it's of 1 sheet because the 2 sides connect. And what I mean by 2 sides is that we could have a hyperboloid of 2 sheets, meaning these hyperboloids do not touch. And again, it's split off into 2 different surfaces. That's why it's a hyperboloid of 2 sheets. We also have a paraboloid. Looks like this bowl-looking figure. And the last one that we have is a sphere. So these are some of the common surfaces that you will be analyzing and that you will be working with as we move through the semester. On the quiz, I am going to show you pictures of surfaces in RSpace 3. And what I did is I embedded some of these GIFs, or GIFs, however you want to call it, onto your quiz. That way you can get the full 360 view of this surface, and then you can go through and identify it by name. What is that surface? On your homework, you will have to identify surfaces based on equations and based off of their geometric views. So make sure that you are well accustomed or well acquainted with observing these surfaces, and more specifically, how to look at some of those traces. That way you can try to visualize what these surfaces look like more accurately in RSpace 3. So that's actually going to wrap it up for us here in this particular section where we were talking about cylinders and quadric surfaces. So I hope you all enjoyed this lesson, and I will see you all next time.